In this section, we're going to look at the definition of the phonemes or basic sounds used in speech in rather more detail. Phonemes are specific mixes of sound frequencies in specific orders. And in the ear, different frequencies are detected at specific points on the cochlea, which is a spiral structure located in the ear. Hence, genetic information can specify that certain combinations of points on the cochlea are connected to individual neurons in the primary auditory cortex. Genetic information then guides the creation of connectivity between the columns that get inputs appropriate for phonemes and the components that implement what I will call attention behaviors, and I'll get to what exactly these behaviors are in a moment. Genetic bias also establishes connectivity from columns discriminating between phonemes to components corresponding with speaking phonemes. This bias could include a tendency for the connections to be established between receptive fields and components for the same phoneme, but as we will see in a moment, experience can also establish or enhance that connectivity. There's also genetically controlled connectivity from the discriminates phonemes area to the discriminates activity overlap area. Then there's connectivity from columns in the activity overlap area with these inputs to a reward component. The reward component targets the inputs to the speak phoneme components. In other words, the reward component can increase the recently active recommendation weights into the speak phoneme behaviors. So now let's look at how this genetically defined connectivity can interact with experience. Suppose a phoneme is heard by the brain of a baby. The sounds will activate some genetically defined receptive fields. An attend to phoneme behavior is activated, and the first step in this behavior is to prolong the activity of the columns. In addition, the columns have genetically guided targeting to a range of speak phoneme components. And let's say one of them has the predominant input recommendation strength at this point in time, so it's spoken, and the baby will hear its own voice speaking. But let's suppose it's not the phoneme the baby heard a bit earlier. So the activated columns will be different from the ones activated earlier, which are still active because their activity is being prolonged. At this point, the activated attention component acts on the outputs of the two populations. These two populations that correspond with hearing the externally spoken phoneme and hearing the phoneme spoken by the baby itself. The action of the component, the attention component, is to synchronize the outputs from those two populations at the input level to the activity overlap area. That will drive receptive field detection in that area. The receptive fields corresponding with little overlap have genetically defined recommendation strengths in favor of a negative reward. They will be the ones that will be detected at this point in time because the phoneme spoken by the baby was not the same as the phoneme it had heard a few moments earlier. The negative reward acts to reduce the recommendation strengths in favor of speaking the selected phoneme, meaning that some other phoneme will be spoken in the future if the original phoneme is heard again. Of course, if the baby's phoneme had been the same, many of the columns activated in the discriminate sounds area would have been the same for both sounds, and different columns would have been activated in the activity overlap area, reflecting that higher degree of overlap. And these different columns have genetically defined recommendation strengths in favor of a positive reward. A positive reward would make speaking the same phoneme more likely in the future when that original phoneme was heard again. In other words, all this genetically defined bias on connectivity tends to result in a baby imitating phonemes that the baby has heard.